Hi, I'm Lance,
I'm Hayden.
and this is Dylan. We don't know where he's at. I'm sure he's doing something awesome like saving babies from a burning building or something, but he's not here right now. Anyways, today we're going to talk about continuity.
Continuity. The informal definition of continuity is a function that is continuous at x equals a if the graph of f contains no holes or breaks at x equals a. In other words, the graph near x equals a can be drawn without lifting your pencil off the paper.
The second part of continuity can be described in a formal definition. The formal definition is a function f is continuous at a if the limit as x approaches a of f of x equals f of a. If f is not continuous at a, then a is what is known as a point of discontinuity.
Next, we have the continuity checklist. The first thing on our continuity checklist is if f of a exists. And this is when f of a does not exist, which makes a function discontinuous. In this graph, the function is discontinuous at a because f of a does not exist.
The next thing on our continuity checklist is we have to make sure that the limit of f of x as x approaches a exists. So, per se, we have a function. It's going, it's doing its thing, and then it goes down at a. So, on this side, it's coming, it's doing its thing, and then vertical asymptote right there. Since there's a vertical asymptote at a, the limit does not exist, meaning the function is discontinuous.
And for our third part of our checklist, we have to make sure that the limit of f of x as x approaches a is equal to f of a. Even though we do have a limit that does exist and a value for the function, if those two do not agree, then the function is discontinuous. As you can see here, the function does have a limit at this point here, c, but the actual value of the function at point A is not equal to c. Instead, it's equal to this point up here, which means this function is discontinuous. So here we have a piecewise function that's both continuous and discontinuous. If you see here, as it comes from negative infinity to negative a, the limit of f of x exists at every single point. There's a value for f of a at every single point, and the limit and the value agree on every single point. But when we get to negative a, the limit does not exist anymore, which means that there's a discontinuity right here at negative a. But as we see from negative a into infinity, it is continuous because along this line, there's a limit at every single point, there's a value of f of x at every single point, and the value and the limit agree. So that means that f of x is continuous from negative infinity to negative a with the negative a included, and then from negative a into positive infinity without the negative a included.
And finally, we have three other rules of continuity. The first one is a polynomial function is continuous for all x, meaning any polynomial function is continuous. Second, a rational function, or a function in the form of p over q, where p and q are polynomials, is continuous for all x for which q of x does not equal 0. And finally, if g is continuous at a and f is continuous at g of a, then the composite of the function f times g is continuous at a.